So welcome everyone to the Air-Sea Fluxes from Space webinar series. This is a new series that continues the tradition that we established for the Winds and Currents webinar. And it will run under the auspices of OASIS as we get the details started. But we're just getting started today, and we're really happy to have Charlotte DeMott kicking this off, talking about the Air-Sea Transition Zone study that just released its final report. So I'll let you take it away, Charlotte.
Okay, thank you, Sarah. And thank you for inviting me. I hope this gives you a good overview of what our group thought about for basically the past 18 months. This ended up being what felt like a pretty grueling process. And I think when I get to the slide where I show you what our committee was charged with, you might understand this. But so today, first of all, this talk is based on briefings we had given to various program managers previously. So, but it's kind of a nice framework for summarizing what has come out in the report, the cover of which is shown on the right. So I'll give a little bit of a discussion of the motivation and what the interagency charge to our group. We talked about how we went about defining observational and modeling needs for the Air-Sea Transition Zone, assessing available current and needed technologies, and then coming up with a roadmap for how we can close some of these gaps. Let's see, there we go. Okay, so just today I want to, as I said, summarize the findings of this report, introduce the concept of the Air-Sea Transition Zone, and then get any feedback or field questions from this group, especially as it relates to Odyssey. So the figure on the right is just a very simple cartoon of what we mean by the Air-Sea Transition Zone. It's essentially the marine atmospheric boundary layer, the ocean mixed layer or ocean boundary layer, and their interface. And we were charged by NASA, NOAA, NSF, and ONR to develop a well-defined strategy to advance observing and modeling capabilities, as well as understanding of Air-Sea interaction at all scales required for harnessing Earth System Prediction, or ESP. So when I was first asked to join this group, to me, it just felt daunting. I thought, how can we possibly do this in 1 year? And as it turns out, we couldn't do it in 1 year. It took us closer to 18 months to get the job done. But the figure on the right just shows you some of the reasons that this was so complicated. There's a multitude of processes occurring in both the upper ocean, at the Air-Sea interface, and in the lower atmosphere. These processes all influence one another, and we needed to think about what observations are needed to better understand the communication between ocean and atmosphere across the globe and across scales. So I first want to touch on just the need. Why do we need to study the Air-Sea Transition Zone for Earth system prediction? And I think it helps to remember that the real motivation for this study is better understanding and modeling for the protection of people, property, environmental resources, both now and in a future climate. So these are just some pictures of ASTZ affected phenomena or related phenomena that affect people. So we have atmospheric rivers, hurricanes, wildfires. This image, third image on the top, is the fires in Maui recently. Drought, which can impact agriculture, and then changes to sea ice, which can be both beneficial for shipping, Arctic shipping, as well as problematic for ecosystems and future climate states on the Earth. So if we think about this more, why do we need better understanding and observations of the ASTZ? Really, the ocean mixed layer and marine atmospheric boundary layer communicate on all scales that affect weather and climate. So on faster scales, they communicate via surface fluxes. This can regulate atmospheric boundary layer potential energy and cloudiness, as well as ocean stratification. And on longer scales, the ocean circulations can then alter patterns of sea surface temperature, convergence, and atmospheric circulations. And so how do current ASTZ observing strategies hinder Earth system prediction? There's an overall lack of process understanding for parameterization development and improvement. Our observations of the AST tend to be sparse. They are limited spatially and often of short temporal data records. This is a problem for efforts to develop coupled data assimilation strategies, as well as satellite retrieval validation efforts. For the purposes of Earth system prediction, there's also often a data latency that even if these forecasting centers would like to incorporate some of these observations, oftentimes the observations are made available too late for forecasts that need to be initialized. So this is a list of the 17 individuals who formed the ASTZ study group. We are a mix of atmospheric scientists, oceanographers, modelers, observers, people focused on process understanding, data assimilation. We represent academia, national labs, as well as private industry. So it was a lot of work. Oftentimes it felt like 17 people in some ways wasn't enough, but because the level of expertise on some subjects was, it's hard to cover all things of the ASTZ with 17 people, but I think in the end, we ended up doing a pretty good job. So we were charged to do these 6 things: to identify current capabilities and key gaps, assess the relative importance to Earth system prediction to resolve various space and time scales within the ASTZ. We were asked to build upon recent and potential future advances in sensor and platform technology when considering ways to improve the observations of the ASTZ, as well as to explore possibilities of using machine learning tools, data assimilation to sort of bridge some of the gaps between models and observations. We are to liaise and coordinate with other relevant US and international activities, such as these listed here. And then finally, to produce a strategy document, which is what was just published last month. So at this point, I'm going to give just a brief overview of some of the content of this report. The 3 main chapters are broken down as you see here. We have a chapter where we define needs. Then we evaluate current capabilities and gaps in our capabilities, and then we discuss an implementation plan. So I first want to talk about methods we use to define needs. We considered needs as defined by regions, purpose, whether this is data assimilation, process understanding, parameterization development, modeling activities, different scales, as well as phenomena. So one way we define needs was to ask what are the scientific needs that drive the system requirements. So as I said, we considered processes and phenomena, space and time scale, as well as region. So these are some examples of the processes that we considered for defining observing needs. Surface fluxes and the sea state, cloud processes, because the clouds couple the ASTZ to the free troposphere and weather and climate disturbances, as well as ocean boundary layer and marine boundary layer turbulence and mixing, including their vertical profiles. And we also considered observing needs for extreme events, such as atmospheric rivers, tropical cyclones, marine heat waves, etc. We also considered scales that define needs. This is a figure from Megan Cronin et al. 2019 in Frontiers. The scales that define needs, of course, vary with the scale. So there are mesoscale and smaller phenomena in both the ocean and atmosphere that require better observation. Seasonal subseasonal to seasonal variability involving phenomena such as the Madden-Julian oscillation, and then interannual and longer time scales. So the needs span all of these scales. And finally, we considered regions that define needs. This is a figure also from the Cronin paper highlighting different areas across the global oceans where more observations are desirable. These include high latitude regions, including ice margins, ocean shelf processes, eastern and western boundary currents, as well as tropical stratification and equatorial upwelling. And so what I have here are just to show you, I tried to pull out some examples that might be relevant to this team. And so Odyssey is focused on ocean surface winds and currents. And some of these considerations sort of project onto our need assessment. And so one example is the role of surface fluxes and MJO teleconnections. So if you have MJO convection situated here in the Eastern Indian Ocean, that convection is about 10% of the energy export by convection with the MJO is replenished by surface latent heat fluxes. So knowing the surface flux, which is largely dependent on surface winds, is one key component for understanding processes that maintain the MJO. Its upper level divergence, which is shown here in these black arrows, interacts with the mean jet stream and introduces these teleconnection responses shown here in the blue arrow. If your model or perhaps your observation suggests a bias in the surface fluxes, you could end up with a too large MJO heating anomaly, too large upper ocean divergence, and an erroneous MJO teleconnection response. So another example, and I apologize for the poor quality of this image, is the interactions between the MJO, its low-level westerly wind bursts, that develop in the Western Pacific. They can lead to the formation not only of downwelling ocean Kelvin waves, but also these surface fresh jets that can persist for periods longer than their wind forcing. And so this represents an upscale influence of intraseasonal winds, upscaled through a surface fresh jet that can then affect El Nino onset. And then finally, a more mid-latitude example, this is from a paper that I just came across yesterday when I was working on these slides. If we look at Western boundary currents and their role in the extratropical transition of tropical cyclones. So when tropical cyclones propagate northward, oftentimes when they cross over the Gulf Stream, they transition from a warm core system to a cold core system. The implications of this are an expansion of the wind field and its related hazards and increased risk to mid-latitude populations. So again, trying to tie in some of these ASTZ process understanding to the implications for Earth system prediction. And so the study noted that extratropical transition is favored both when the SSTs are relatively cold, as shown here on the left, but also when the fine scale SST gradients associated with ocean eddies are relatively large. So processes that maintain these eddies and the sharp SST gradients associated with them can have upscale influences on the behavior of these tropical cyclones that can impact people. So through this assessment, some common scientific needs emerged. They can be sort of broadly defined in terms of the need for thermodynamic, kinematic, and flux profiles of the ASTZ. So vertically resolved measurements throughout the ATCZ. But there's also a strong need for co-located state variables, such as near surface temperature, humidity, sea surface temperature, winds, currents, and precipitation globally for budget studies. And this is really where the satellites, the need for satellite retrievals comes in, as well as in situ measurements for validating those retrievals. And then also there is sort of a separate need for strategies for observing the ASTZ during extreme events. And modeling needs are listed here separately. I'm not really going to talk about those too much today. So moving on to evaluating capabilities. This ended up being a pretty long and detailed chapter, and I'm just going to give you a very high-level overview here. We considered 5 sublayers of the ASTZ, and so they are the marine atmospheric boundary layer, the wave-affected surface layer. So this is the layer where ocean surface waves affect the stability and thermodynamic properties of the lower atmosphere, the air-sea interface, the wave-affected ocean surface layer, and then the ocean boundary layer. I may have already said, you'll see me go back and forth between OBL and OML in this talk. They're referring to the same thing. It's just that our nomenclature is not consistent yet in the slide deck. So for the sampling needs, we would like sustained, coincident, and co-located measurements of the ASTZ throughout these 5 sublayers, both for process understanding, coupled data assimilation and development. Current capabilities for these observations include in situ instruments, platforms, and methods in use today. So we already have some capability for collecting these measurements, but our needs are for advances in instruments, platforms, and methods to improve the vertical resolution of these measurements, both in and as well as getting them more co-located in time and space. And so there are different capabilities and needs for different parts of the ASTZ, and there's also different capabilities and needs depending on whether we're talking about vertical or horizontal sampling. Okay, so I think, and this, I don't want to spend too much time on this. I'll just highlight that at the interface, some of the needs that we see moving forward are measurements of directional wave spectra measurements, concurrent with estimates of winds, currents, and other ASTZ variables. And some of these satellite missions that you see listed here are seen as being helpful for closing this gap. Okay, so this idea of co-located coincident state variables globally, this is really where the satellite community fits in. So the column sampling approach really is intended to be at certain key locations, whereas the global sampling will rely heavily on both satellite measurements and a network of in situ observations. So our current capabilities, there are some surface-based measurements, such as the NOAA GDP Global Drifter Program and the Argo drifters that collect information about the ocean, mix their depth, but it lacks extensive measurement on airside variables. We get some of this from moorings, but they're highly concentrated in the tropics, and there's a lot of important regions of the world that are poorly sampled. Satellites can help us with this. They are but in some cases, their measurements are not co-located or coincident, but they have the advantage of global coverage. And so this identifies some needs for the globally extensive measurements. And just to highlight some of the needs here, this slide is from a different presentation where we were mostly focused on temperature and specific humidity and the boundary layer from satellite. This is one area that could use improvements in measurements. I know that's not the focus of Odyssey, but we could also talk about the need for improved wind and surface current measurements that Odyssey could help backfill here. Okay, so moving on to the roadmap for this observing strategy. Okay, I think I'm doing okay on time. So we have 4 broad implementation strategies. And the first one is that we need to develop an observational and modeling technology for coupled ocean atmosphere prediction. And so this really, we've really in the report emphasized that this needs to be bigger than any single agency. And it needs to move, it's sort of like saying it needs to move from a research to operations type of progression. So many of the available in situ observations of the ocean come from individual research projects, something like 70% versus global sustained programs such as NOAA GDP or the Argo drifting array or the tropical mooring arrays, and a few others throughout the globe. And so our first recommendation is that we need to really consider a bigger multi-agency or organizational layer above any given agency that would have strong international collaboration with other countries to sort of achieve this observing strategy. More specifically, though, we feel that we need to develop observing sites of the ASTZ where we can resolve the ocean atmosphere coupled processes across scales for an extended period of time. So if you want to understand the interannual, these upscale effects, you really need to collect these observations in a single place in a coordinated manner for an extended period of time. So that's sort of like selecting a few key locations to do this type of measuring. On the other hand, skipping down to this bottom one, we also want to develop a global observing network to measure key air-sea coupling variables. And this includes some of the foci of out of sea, the surface currents and winds, which are key to understanding some of these, the drivers of these ocean mixing processes that affect the ASTZ. And then as well as expanding observations of extremes such as tropical cyclones, ice edges, both extreme weather events and challenging regimes, including high winds, sea ice, etc. So just to give a little more detail on these four strategies, strategy one is to develop observational and modeling technology for coupled ocean atmosphere prediction. There needs to be sort of a large umbrella organizing structure that will support the development, testing, and deployment of sensors and platforms. And this, we feel like this really requires a new paradigm to sort of provide an end-to-end management of this strategy. We would like to utilize model experiments to inform the observing system design. This should be done in tandem with the development, testing, and implementation of coupled data assimilation. And an important component of this is that this strategy one should have a very clear practice for collating and providing and disseminating the data that is collected. It should be almost automatically sent to modeling. Our vision is that the data collected through these observations would be readily shared with modeling centers to be incorporated into forecast models. Okay, so strategy two, to observe the ASTZ in strategic locations, we want to deploy suites of co-located observations at key sites. So again, this is the figure from Cronin et al., indicating various regions in these boxes where observations are needed. In some cases, observations exist, but there are a lot of these small boxes that don't have these tiny black boxes in them. So we want to, at these locations, we really want to focus on the vertical profiling of scalars, turbulence, and fluxes, as well as their variation across sharp horizontal gradients, for example, at western boundary currents. And again, we want to capture the cross-scale interactions and full parameter space with these long time series. And so what this might look like, this is a figure used in our report. It's based on a figure from Caroline Clayson's poster describing supersites. So It would be helpful to, we feel it would be helpful to coordinate with industries such as offshore wind energy or even ocean drilling programs, industries that have a lot of experience in building platforms and leveraging some of this platform technology to support instruments that would be mounted directly on these platforms, but also to provide docking stations for recharging for some of the more recently available autonomous vehicles that could help achieve this vertical sampling profile. So strategy 3, expanding the observations of extremes and challenging regimes. We would like to see development of a rapidly deployed, targeted, and coordinated ASTZ observations of high impact extremes. And so this would include phenomenon such as tropical, extratropical cyclones, atmospheric rivers, marine heat waves, marginal ice zones. The idea would be that when forecasts show the possibility for an extreme event, for example, if you consider a tropical cyclone that may be undergoing rapid intensification prior to landfall, it would be helpful to be able to deploy assets that could better sample the ASTZ to help really better initialize forecast models to help get a better understanding both on the hurricane track and its relative intensity as it approaches land. And there are other examples, of course, for atmospheric rivers, marine heat wave events, but that's just one example. Okay, so strategy 4, this is again what probably is of most interest to this group, to develop a global observing network to measure key air-sea coupling variables. And so we argue that it's important to support both current and possible future satellite and suborbital remote sensing missions. This type of information is going to be critical for diagnosing budgets and flex parameters, including measurements of waves, temperature, humidity, wind, currents, boundary layer height, precipitation, and radiation. Examples, again, SWOT, Odyssey, and Butterfly missions, which would be helpful to collect these needed measurements. And so that's sort of from the remote sensing standpoint, but we would like to complement this with in situ distributed networks. And so one idea is to really first build upon the networks that already exist. So NOAA GDP and Argo, I'll show you a picture in a minute, indicating some of their global coverage. These two programs are highly focused on ocean variables, and there's you can get information on currents from these, of course, especially with the NOAA GDP. Some of these drifters are drogued at some are drogued, some are undrogued. So some reflect more surface currents, some currents at slightly lower depth. But there's also sort of a dream that it's like it would be wonderful if we could equip some of these assets with sensors to measure boundary layer quantities such as temperature, specific humidity, even winds, to help provide ground truth measurements for satellite retrievals. We have moored moorings. We would like to see these in more diverse locations because there are parts of the world, as I showed earlier, that where we simply don't have enough in situ observations. And then data assimilative models to tie all of these together and help remove some of our blind spots where our observations are sparse or don't exist. So this is just a picture used in our report. I believe the blue dots you see are, I believe these are the GDP, the Global Drifter Program drifters, and not Argo arrays, but I can't quite be sure. But this is an example of the types of drifters that are out there, and also moorings that you see in triangles. All of these assets collect different types of measurements. Their measurements tend to be more heavily weighted to ocean observations, so the air-sea interface and lower. And it would be nice to sort of embellish these assets so they could collect more measurements of the marine atmospheric boundary layer. That's a huge challenge, I think, in understanding some of these coupled processes. So we've developed a 10-year roadmap for each of these strategies. And I'm not going to go through each individual strategy, but the basic outline is an example of which is given here. In years 1 and 2, there should be interagency coordination to identify current and near future observing capabilities and to assess their importance for Earth system prediction. To start to flesh out some of these strategies and what is needed to get there, to leverage interagency coordination, for example, among US CLIVAR, ICAMs, to support process studies to produce system recommendations. And then during years 2 through 5, to really have an intensive field work and testing period to see what of the new and emerging technologies can be upscaled to sort of fill some of these needs. And then the implementation in years 5 through 10 is just really to get it done, go global, start working with your international partners, relevant US agencies. So it's a big ask. We've noted in the report that while we feel it's important to proceed through the roadmap in a sequential manner, in other words, don't skip to phase 2 work before completing phase 1 work, each of these 4 strategies could be implemented on its own timeline. So to some extent, they're all related, but they could be attacked individually. And so that's kind of where we are with our report. And I think that's about it. So with that, I can take questions from you.
Thank you so much. This was really wonderful. I will say, I really love the fact that you emphasized Odyssey, but our goal in moving forward in this webinar is to take a multi-satellite approach. And
Great.
there are people online who are representing some European satellites that do much higher resolution measurements that maybe are geared to process studies. And I'm wondering if the report addresses any of that.
We do talk, yes, we do talk about some of the other, and so thank you for that clarification. I was I misunderstood the full audience of this talk. So it's great. And yeah. So we do in the report, I think in sections that were led by Carol Ann, talk about some of these other satellite Harmony, I believe, and as well as others. So yeah, it's not intended. So we were funded to do this study by US agencies. So there's probably a greater emphasis on some of the proposed US missions, but there's definitely in the report some discussion of how this can be leveraged with satellite missions from other countries as well.
That's really great. I see that Eric Desaro has his hand up, and I also want to encourage anybody else who has a question, and especially early career people, to speak up. So, but I'll let Eric go ahead while other people think of questions.
Yeah, hi, this is fascinating stuff. Thank you guys for doing this. Something that I've been thinking a lot about actually in the last, well, I didn't even know that this was happening, but that's fine. 2 things which I wondered if you thought about at all, which strike me as pretty strong issues. One of which is the issue of silos. I've been involved in a lot of things that are air-sea interaction-y, and usually, you've got a bunch of. Usually, it's either sponsored by the oceanographies or sponsored by the atmospheric. There's lots of difficulty in communication between atmospheric and oceanographic people, and so it seems to me there's a real need for the one thing that's holding us back on this is just people that are thinking about the system as a whole, as opposed to just thinking about their side of the interface. And I And there are things like metrics. I mean, for instance, I think of Adam Rybeck has a metric that spans both boundary layers.
Yes.
And there's a whole set of intellectual things that need to happen to really think about coupled things. Another way of saying it is we have coupled models, but we don't have we have very few coupled scientists. And I don't know if you thought at all about that issue.
Yeah, we have thought about that a lot, and I really appreciate your comment because it's something very near and dear to my heart. And in fact, I wish I had included a slide to include the statements we made in the report, both in our executive summary section and in our conclusion section. We really talk about the need. So for a new paradigm. And that was one of the motivations for including the new paradigm right in the title of the report, is that we need to think about the ASTZ as a single entity. It is two boundary layers that are firmly interlaced across the interface, that are constantly exchanging energy and matter, gases, etc. And so an oceanographer would never limit their study of oceanography to just how does sea surface temperature evolve. An atmospheric scientist would never limit their study of atmospheric science to just how does rainfall evolve. If you really want to understand those, what causes those two, and so atmospheric scientists often don't look beyond sea surface temperature. If you're an oceanographer, you want to know about the surface wind, rainfall, etc. But to really understand and make progress, we need to observe, think about, and train future scientists to think of this as a single entity. So that's, yeah, I appreciate your comment. And yes, and even funding agencies, there are proposals. I've submitted proposals before, and it's like, well, I don't know for example, which division of NSF to submit this to, because it involves elements of both. And even sometimes submitting a paper on a coupled ocean atmosphere process, you can be surprised by the number of reviewers who are, sometimes the reviewers are weighted more heavily towards one sphere than the other. So yes.
Great. I see that Megan has her hand up.
Yeah, hi, thanks. Great talk, Charlotte, and fantastic to see so much progress. Just to follow up on Eric's comment, it seemed your study team were all physics. And so from the OASIS, that's the UN Decade Program, Observing Air-Sea Interaction Strategy, we have taken the approach that we really have to have a holistic view of perspective of the entire energy cycle, water cycle, carbon cycle, life cycle at the air-sea transition zone. And really, as we develop these 10-year plans for, monitoring carbon uptake in the global ocean, or, all these different typically siloed activities, as Eric says, we have to be, really working together, and that none of these plans will work unless we're all doing it as one big bundle. And so how are you doing that approach?
Yeah, I think
from
that's
a pure physics side here.
right. And so I think that's a fair criticism of the report, is that we are focused on the physics of the coupling. And there has been less emphasis on the ocean biology and biogeochemistry.
Okay, but maybe.
But yeah, I think some of these recommendations, so for example, super sites, they're super sites because they have the ability to host multiple types of observations. So I think that is one opportunity to say that, yes, we can equip the, both moorings, super sites, et cetera, to measure some of these variables that influence, say, the CO2 flux or oxygenation and such. But yeah, I think that's definitely a fair criticism of our report.
Okay, I have one more question. Can I ask that? Okay, so your study group is a 1 year, went on for 18 months, and now you're done, I guess. But I'm really hoping that you will continue the implementation of this and have this as a living document through working with OASIS. At least OASIS would love to have this as, be able to run with this.
Yeah.
And so what is your plan for connecting for the future?
So our plan for the future is we have, I believe, 2 briefings scheduled. One is to the interagency group who essentially commissioned the study, and also to ICAMS. So, but I think there's a statement at the end of the report that this is our recommendation, and what is needed now is more community discussion and feedback to the funding agencies to develop plans to carry out some of this. Now, there are probably people on this list who are involved in OASIS to some degree or another. But I think OASIS in particular is going to be an important organization for us to continue our discussions with. Since when we first started this, we actually struggled to come up with, well, how is what we're doing any different from what OASIS has recommended? So there's a lot of overlap between what you'll find in this report and in OASIS documents.
Which is fantastic.
Yeah.
Because in fact, this is actually the community going out and doing the work. I mean, OASIS is a bottoms up organization. And so it's just trying to connect the dots of all of this work.
Yeah, and so really this report was, it was the outcome of several community workshops that over the years, 3 or 4 community workshops at least, plus other input that routinely and consistently said we need to better observe the air-sea transition zone. And we need to do a better job of understanding how those observations can be leveraged for coupled forecast models. And so I think that message certainly was heard by the agencies. So yeah, we certainly hope that if they said, yes, we need to know how to do this, that there will be continued action on this. But I'm sure it requires continued pressure from
advocacy,
yes,
community work. Good.
See a couple more hands up. Let's let Anish go. Subramanian.
Thanks, Sarah. Thanks again, Charlotte. Great presentation, and thanks for all the work over 18 months to the whole team. I was wondering about the different ongoing efforts that are at different stages of development. For instance, on the satellite side, Odyssey, they have their proposal, and Sea Star, Harmony, Butterfly, they're all at different stages of proposing their missions, as well as ongoing efforts to organize field campaigns that would observe the ASTZ, right? Where would all of that fit in within the roadmap that's been proposed in the report? Because I see that the roadmap is proposing like new efforts that would organize the community around field campaigns, around future missions 5 years down the line. But there is already ongoing efforts currently. How would those slot into the roadmap that's been proposed?
Yeah, so there was some discussion of specific proposed satellite missions. And you're right, those are kind of proceeding on their own trajectory, I guess.
Right.
And I think some of that coordination will have to be sorted out as the agencies decide which of these strategies to attack first or address first. So we didn't really, we did make a strong case for something like a butterfly mission that would include the coincident and co-located observations of all variables needed to estimate the flux. So if you can do that, you really simplify and remove so many assumptions that you have to make regarding, the lags. If you measure the wind at this location at this time, what can we infer it is when we get around to measuring, or retrieving boundary layer temperature and moisture from this satellite. So we talk about that some, but I don't think we made any very strong for example, we didn't say you really must fund this, satellite program or another. We sort of felt that was beyond our charge, really.
Yeah.
So we did mention several that are at various stages of the proposal process that would be helpful for achieving some of these goals.
Okay, great. Thanks. Okay.
And Mome.
Yeah, thanks for the great overview. You mentioned several times that that's supposed to be a segue to improve predictions and climate system models. But in the ideal case that we have all these beautiful observations of the complex stuff we see at the interface, I think the models are not able to observe them, to implement them. So there was a small section about the modeling component there. But what is, like, as far as I understand how the FSC interface is modeled, they're just not, like, there's so much complexity in the system that I'm not actually sure if our current way how to model it is able to actually represent that complexity.
Yeah, that's a really good question, and I certainly sort of glossed over some of this. So not all observations, of course, can be assimilated into models, but what some of these observations are needed for validation for example, LES and DNS modeling studies that form the basis of parameterizations in models. So surface flux parameterizations are actually, I think they're one of they may be an exception in coupled models, and that their parameterization actually is built upon in situ observations. For many other processes, such as ocean mixing, boundary layer turbulence, cumulus parameterizations, those parameterizations tend to be built on large eddy simulations because there's really no way to collect the measurements at a fine enough resolution and over a large enough domain to develop the statistics needed to come up with the parameterizations of these subgrid scale processes. However, you still need observations to validate the parameterization and even the large eddy simulations. So the observations are needed for model improvement efforts in a few different ways. And you're right, I don't think coupled forecast models are going to include directional wave spectra, for example, but it will probably, it probably has improvements of the surface flux algorithms can be built upon some of those observations to help us better characterize how does the wave state change as a function of low level wind and stability conditions, how does that affect the flux? And I think the core algorithm is one that take some of the wave state into account. And so it would be nice to have observations of that over a broader range of background conditions to ensure that the parameterization is doing what we want it to, or that we intend it to.
Yeah, can I answer shortly? I think I agree with all of this, but I think what I wanted to point at is that this divide that Eric was mentioning and the need for a new paradigm that is outlined in this Cliver paper extends to the modeling community, right? So there's atmospheric modelers, there's ocean modelers, and if you want to treat this as one system, then like the coupling has to be way more consistent. It's very simplified what's done there currently. Yeah, I think so. If we want to make you, and I think it would be nice to see if the modeling community reaches, if it comes from the modeling community to the observational people, that they describe the need, what's need to be observed, right? It's not going like that. The effort actually comes, or the demand comes from the modeling people rather than from the observationists.
Yes, I would completely agree with you there.
Thanks.
Thanks. I see that Claudia Pesquero has her hand up.
Thank you very much. You discussed that the ideal case would be observing globally and on long time scales for several years. And you also discussed the fact that we need many different scales and to be able to go across actually the scales. Did you also discuss the spatial and temporal resolution that is ideally required for this kind of observations or not?
We talked about that some, and we didn't. Yeah, so we recognize the need for characterizing the temporal and spatial scales, but we felt like it was a bit beyond our charge to say we need these observations at this scale, or at this resolution and at this frequency. So yeah, we did stop short of specifying that because I think really because we felt like our 17 people didn't have the full breadth of expertise to really address that. I think a group like this is probably better equipped to provide guidance for that. But it should also, as was just mentioned, be discussed in coordination with how could this help Earth system prediction and modeling needs.
Thank you very much.
Thanks. I should say that Claudia is one of the air-sea interaction leads for Harmony. So
very
she's
good.
thinking about very high resolution capabilities that Harmony will deliver.
That's great.
Which is really quite a contrast with what Odyssey or Butterfly could do on a global scale. And so it's wonderfully complementary. Jim Edson has his hand up.
Yeah, hi folks. Great job, Charlotte. Always enjoy listening to you give talks. So I just wanted to, remind folks, you've now got an air-sea interaction guy running the Ocean Observatories Initiative. And as a result, the flux products that are coming out of the moorings are going to be vastly improved. That's one. But those are just the ones, that's a sonic anemometer that's giving you momentum and buoyancy fluxes, basically. I'm not allowed to point at anyone in particular when I make these sort of requests, but it would be awfully easy for someone to put an IRGA, an infrared gas analyzer, on these moorings as well, so that we can get latent heat and then also get separately sensible heat from these mooring measurements. So it's just something to keep in mind. While you're going to have a champion if you submit proposals to NSF, from my perspective. So anyways, there are things like that we could take advantage of. There are other things like we go to sea, even though we put moorings out or cables, etc. We do use ships a lot to turn these moorings, etc. Wouldn't it be great if we always went out with balloons to launch every time we go to sea? What the value added to these flux measurements and our subsurface measurements if we had so I can only imagine the modelers just totally digging that idea, right? And that would be us working with NCAR, for example, or some ideas like that. And then the last thing I think is really important, I love the concept of BGC Argo, for example. And this is this question of so much physics. Well, there are a number of us that are measuring things other than just physical processes like CO2, pH, et cetera. But man, those are the devices that really need work. And so using these various platforms as a test bed for new technology to do a better job of getting, say, subsurface CO2. We're doing it, but it's a tough measurement. It's a tough measurement to maintain, to interpret. It takes people and humans in the loop to get out that, really hard-earned, awesome data. So all of these things are, look to not just OI, but all of these sites, Megan's PMEL moorings, things like that, where we can start to add these really critical components and really start to make progress, not just on the physics, but also on the biogeochemistry. And I do think this is happening, and where I see it is early career scientists. Keep it up, encourage them. I mean, they're putting together one group just got Goose endorsement for a biogeochemical, basically playbook. Hillary and others and Sophia are working on that. So I say go young people. There are opportunities, just if you go down that path of using some of the available biogeochemical data, et cetera. So good job. I love this, Charlotte. So well done.
Thanks.
Thank you, everyone. Thanks especially to Charlotte. We are at the end of an hour, and I want to make sure we wrap up and let people get on with what they have to do next. But this has been a really wonderful start to this new series. We're hoping to showcase some of what CSTAR might do coming up. So still trying to get things scheduled, but stay tuned, and we'll hope to have more discussion in the coming weeks about this whole range of topics. So thanks, everyone.
Thanks for having me.